Mr. Susinder, founder and CEO of Swinovate, is one of the most experienced people in the Wi-Fi industry. Through his courses and workshops, he's helped many professionals finally make sense of Wi-Fi. And today, he's here to share those insights with us on OFDMA.
What is OFDMA and how does it differ with traditional OFDM?
Wi-Fi started using OFDM since the 11G amendment. Actually 11A it introduced in 5 GHz, then it came to 2.4 GHz as well with the 11G amendment.
Why so much time? So are there any practical challenges involved in getting OFDMA in Wi-Fi, or was the industry focused?
I think mainly it was the industry's focus on just getting the throughput, getting to high throughput like several megabits of throughput consistently in a challenging multi-path environments.
The AP that's actually reaching the random count 0 and winning the medium, but the ones who are transmitting are the clients. Isn't that unfair to the AP? Isn't it losing chances on downlink transmission?
Definitely it is losing its opportunity because it put all the effort. Clients are using it, which will affect the balance of traffic between downlink and uplink.
What are the benefits that the users can expect when OFDMA is implemented, and in what kind of deployments can we expect those benefits?
Best use case is basically all the traffic that we typically use day in and day out falls in the OFDMA use case only. More clients and then very little traffic for lots of clients. Perfect fit for OFDMA. Practically, the OFDMA, are we achieving the best OFDMA results? Answer is no. And the reason for it is we don't have the proper compute budget available for it. So this is something I think the standard people did not foresee, because usually people who work in standard don't work in product. That's unfortunate reality.
I'll give you a set of features in Wi-Fi and you had to rank them. So basing on the contribution, frame aggregation, MIMO, MU-MIMO, OFDMA, BSS coloring, and then MLO.
Number 2 is definitely mine. First, definitely I will give it to
Hey everyone, welcome to Weekly Wi-Fi Wisdom podcast series, where we talk everything about Wi-Fi and the tech that surrounds it. I'm your host Sainath. I'm WLAN QA engineer at Candela Technologies, and today we have our guest, Mr. Susinder. For Wi-Fi folks, I don't think there is any introduction needed because he is well known in the Wi-Fi community. So we are very well aware about the technical posts that he does on LinkedIn, and he also offers Wi-Fi training sessions through Swinovate. So he is currently working as a CEO at Swinovate, and he's also the founder of the company. So I'm very excited that he is here with us, and thank you for giving us your time, Susinder. And today he is going to talk about OFDMA. Very excited to have you on our show, Susinder. It's an absolute pleasure that you joined us.
Thank you, Sainath, and thank you to Candela for this opportunity.
Yes, let's get started. So, as we are talking about OFDMA, Wi-Fi 6, it is one of the key features, right? OFDMA. To start with the basics, what is OFDMA and how does it differ with traditional OFDM?
Yeah, see, basically, Wi-Fi started using OFDM since the 11G amendment. Actually, 11A it introduced in 5 GHz first, then it came to 2.4 GHz as well with the 11G amendment. After that, several amendments happened. 11N came, 11AC came. Until that point, a lot of the focus was on just getting the peak throughput or higher throughput for single user case, meaning we are transmitting to one client at a time, and we are trying to maximize the single user throughput. So that was the focus. And until then, there was not much focus on network-wise efficiency, like in a multi-client scenario, how the throughput scales with number of clients. Until then, single user peak throughput was the main focus. Now with Wi-Fi 6, what happened was, as people started connecting more and more devices, they started experiencing the inefficiency of Wi-Fi, especially when it scales with the number of clients. So that's why they brought in this OFDMA, basically the idea of multi-user. Actually, the idea of multi-user was introduced in Wi-Fi 5 itself, that is 11AC itself. But they brought in first MU-MIMO or multi-user MIMO. Then they tried to expand the same concept with the frequency domain. So instead of using different spatial streams to send multi-user traffic, the idea was OFDM inherently has orthogonal subcarriers.
Right.
And since that orthogonality is built into the OFDM, we can use different subcarriers for different users. So that will be like a natural way of getting the multi-user, transmission without actually incurring a lot of overhead. If you see the MU-MIMO in 11AC, there's quite a bit of overhead in this. We have to do sounding, and we have to get the channel sounding, the channel state information, feedback from all the clients, right? And that takes quite a bit of airtime. And there's a lot of other complexities involved with multi-user MIMO. But with OFDMA, we don't need all the channel sounding overhead. We can right away schedule a multi-user transmission. So it's kind of a very natural selection.
Right. As you said, we have OFDM from 11A, and we have gone past many Wi-Fi generations, and it took us Wi-Fi 6 to get OFDMA. So why so much time? So are there any practical challenges involved in getting OFDMA in Wi-Fi, or was the industry focused on more on, like you mentioned, on high throughputs? So why so much time gap?
No, I think mainly it was the industry's focus on just getting the throughput. Because getting to high throughput, like several megabits of throughput consistently in a challenging multi-path environments, that was fundamentally the focus until the Wi-Fi 5. Actually, Wi-Fi 5 itself, they started thinking about multi-user, because as I said, multi-user MIMO was definitely introduced. So multi-user idea came, but they didn't really focus on efficiency or network wide, meaning if I have 20 clients, if I have 50 clients, when I have a lot of clients, how the network wise performance is. That was not the focus. That is one point. Technically, another point I would say is the OFDM structure also needed some modifications. So, meaning how many subcarriers we use, that also needed some changes. Because if you have to accommodate 20 users or 30 users, and before in 11AC, we have only 64 subcarriers in 20 megahertz. Right. So 64 subcarriers, if you distribute to 30 users, imagine each user will get only 2 subcarriers, and it will be very narrow bandwidth transmission. And there are several regulatory challenges in terms of having very narrow bandwidth transmissions. Also, if you go to narrow bandwidth, it will start resembling a radar pulse, a radar waveform. So in radar channels, it will confuse the radar signal processing as well. So all these considerations, right? So they had to fundamentally change the OFDM structure, which they didn't want to bring in the 11AC. See, definitely 11N is where aggregation itself in. So those were much more important things to get to the higher throughput. Quality of service was brought in, right, in 11N. So 11N was a big change. 11AC was all expanding on the idea of channel bonding. That itself had not settled, like we were still in 2040, then getting to 80 megahertz, 160 megahertz. So their first focus was, let's get to reliable single client throughput, right? Wider bandwidth, right? That was the focus. Then, Wi-Fi 6 seemed like the right time to start bringing network efficiency as the main theme.
Understood. Yeah. Now, can we talk about how OFDMA works in Wi-Fi 6? Maybe what are the frames involved and what is the procedure? Could you please say? Yeah.
the there are two, multi-user, OFDMA we can do. One is downlink and then another is uplink, right? So
Right.
downlink means AP to client, uplink means client to AP, right? So in both directions, Wi-Fi 6 supports the OFDMA, okay? Now for the downlink OFDMA, what they did was they created a new PPDU format, which
Mhm.
they call the multi-user PPDU format. Okay.
Yeah.
And we have to indicate in the PPDU format itself which are the users which are included in this transmission. So it's a multi-user transmission. So you have to tell somewhere in the frame itself who are the destination, like who are the, because you have multiple receivers now. So you have so what they had was we had this HE sig A and HE sig B. So if you see the HE sig B field includes information about which are the clients for whom the data is present in the payload portion. So this is in the file layer. In the file header, the HE sig B is one of the fields where that is included. Secondly, we also have to include like each user, what subcarriers are allocated, like how many subcarriers are allocated. So actually the technical term for it is resource unit.
Right.
So what is the resource unit, how many subcarriers allocated for you, and where is the location of that RU resource unit. So that has to be specified for each of the users. And the users are identified in terms of the AID or association ID, which was assigned during the association time itself. So all this information is there in the physical layer header. Okay. And then, we can just transmit it, multi-user OFDMA. AP creates that and then transmits it. Clients will look at the physical layer header. They know, okay, first of all, they need to know they are part of this transmission.
Right.
So they look for their AID. If they find their AID present in the file header, then look at the RU allocation. What is the RU allocated to them? Then they will go and extract only those subcarriers.
Mhm.
And then, further processing is the same, like, right? So that is how it works, right? Then we have to get the acknowledgement. So acknowledgement can be obtained in many ways. One is you can fetch them one at a time. Like we can use a block AG request and get one at a time, right? One of the users we can get an immediate block AG, and then for the remaining users we can indicate the delayed block AG and use the block AG bar BA exchange, what they call as bar BA exchanges, but that will require multiple bar BA exchanges. Another alternative is use uplink OFDMA to get the block AGs. So that option is also there. So we can use but that will be a lot more efficient compared to bar BA, multiple bar BA exchanges, right? And as I said, the OFDM structure had to be changed from 11AC. So actually the number of subcarriers was made 4 times higher. So,
Yeah.
so that we have a lot more subcarriers that allows us to distribute that to a lot more users now. So
Right.
I think go up to 37 users. I think in 80 megahertz, you can go up to 37 users in 80 megahertz bandwidth. Okay.
Yeah.
That's on downlink. Uplink works a little bit different. In uplink case, the clients need to know when to transmit that OFDMA frame, right? So that is indicated by a trigger frame. So AP first sends what is called a trigger frame.
Mhm.
This trigger frame is sent, and the RU allocation, what clients have to participate in the uplink OFDMA, that is specified in the trigger frame. Okay, so because trigger in the Mac, there's a specific Mac frame format for it. So there is a Mac frame type specifically allocated for trigger frame. So it is one of the control frame types. So in that, which are the clients that have to transmit, and then what is the resource unit allocated for them, right? In fact, what is the transmit power, what MCS they have to use, what what bandwidth they have to use, how long they can transmit also, even how long they can transmit. All of that information is present in the trigger frame. So exactly SIFS time. Okay, so SIFS is 16 microseconds in 5 gigahertz. In shifts time after receiving the trigger frame, the clients whose AIDs are present in the trigger frame have to respond with the OFDMA transmission. And for that, there is a specific PPDU format also designed for that. That is called TB PPDU, trigger based PPDU, TB PPDU format. So it has to, the clients have to use the trigger based PPDU format, which is slightly different compared to the single user and multi-user PPDU format. So they transmit that. So AP now has the challenge of retrieving all the clients payloads from the trigger based PPDU, because multiple trigger based PPDUs will be transmitted by different clients at the same time, right? And then AP has to send the acknowledgement. So instead of sending the acknowledgement for each of the clients individually, what they did was they came up with a new block ACK format called multi-star block ACK format. So it allows us to aggregate the block ACK of multiple users and then put it together in one frame, right? Instead of having multiple frame transmission, we can have one multi-star block ACK frame which contains the block ACK for all the users. So that is how the uplink OFDMA works.
Right. Great. So in downlink it is MUPPDU, and in uplink it is trigger based PPDU.
Correct.
And in the uplink OFDMA transmission, it uses something called multi-user block ACK, so that AP can acknowledge all users at once, right?
Yes.
Is there any limit on how many users it can acknowledge in that multi-user block ACK?
So that frame format actually is quite generic. They don't have any particular limitation specified there. The limitation really comes from the RU allocation, because there is something called RU plan which is specified in the standard. What are the RU plans that are possible? There are only fixed some RU sizes which are possible. I think RU26, RU52, RU106, RU42, 484, and then 996.
996, yes.
These are all the different options that are available for 80 megahertz bandwidth, for example. So that fundamentally puts a limit on like how many users we can have. The limitation really doesn't come from the multi-star block ACK format. The multi-star block ACK format allows you to aggregate actually many clients. I don't think there is any particular limit there. The limit may be in terms of the payload size. Like we have a generic limit on how much maximum MPDU size that we can have, right? So those limits apply even for the multi-star block ACK frame.
Right. Now here is a question about uplink transmission. So prior to OFDMA, let's say if 3 or 4 stations want to transmit. So the station that would transmit first is the one that reaches its back of counter to 0. Right. So let's say station 1 back of counter is 2 at the moment. Station 2 is on 4 and station 3 is on 6. So basing on the random back of timer, station 1 would ideally transmit, right? And if these 3 are on different, now in uplink OFDMA, if the same 3 stations had to be involved in part of OFDMA uplink transmission, they 3 are on different random back of timers, but do they all transmit at the same time still?
Yeah. So they have to transmit at the same time, because then only the AP will be able to, the transmissions will be orthogonal. See, because the fundamental idea is you are using the orthogonality which is inherent in OFDM to achieve the concurrent transmissions, right? So for that, all of them have to transmit at the same time, and that is a very important requirement. So what they have done in the standard is they have asked that clients do not have to contend for the medium for the trigger based PPDU. What actually happens is AP contends for the medium and sends the trigger frame. So AP contends for the medium and it wins the medium, right? And it transmits the trigger frame. In the transmit opportunity of the AP gives the transmit opportunity to the client. So basically the trigger frame is reserving the airtime for the subsequent trigger based PPDU from the clients. So all the effort is put by the AP, but the clients only enjoy the airtime. The medium is actually used by the client, but AP just sends a small trigger frame and gives the rest of the airtime to the clients. So as you know, we have this duration field, right, which allows us to reserve the airtime using the network allocation vector, NAV, right? NAV timer is used to reserve the airtime, right? So that's what happens. So trigger frame reserves the airtime for the following trigger based PPDU and the multi-star block hack.
Right. So it's the AP that's actually reaching the random counter 0 and winning the medium, but the ones who are transmitting are the clients. Isn't that unfair to the AP? Isn't it losing chances on downlink transmissions?
Definitely, it is losing, its opportunity because it put all the effort and then, clients are using it, which will affect the balance of traffic between downlink and uplink, right? So definitely it will affect it. So that is why they have another provision in the standard, right? You have the standard WMM parameters, right? Which basically the AP advertises, and that tells the contention window parameters, contention window minimum, contention window maximum that the clients have to use, right? That is advertised in the WMM parameters. So when you have OFDMA, in order to ensure this fairness for the AP, what they have brought in is a feature called multi-user EDCA, MUEDCA. So that is a new element that is advertised by the AP in the beacon, right? And that advertises as different set of contention parameters. Different set of CW min, CW max parameters are advertised in the MUEDCA parameter set element. So the clients which have participated in an OFDMA, so let's say a client recently participated in a trigger based PPDU, right? A triggered uplink. Instead of using the WMM parameters, it has to use the MUEDCA parameters. So it has to use the contention window parameters from the MUEDCA parameter set instead of the WMM parameters if it recently participated in a triggered uplink. So in that MUEDCA parameter set, they have given definition of what do you mean by recent. So there is a timer field like MUEDCA timer. So basically that says for example, if you participated in a triggered uplink in the last 300 milliseconds, right? Just for example, right? If you participated in a triggered uplink in the last 300 milliseconds, then instead of using WMM contention window parameters, you have to use the MUEDCA contention window parameters. So what the AP will do is it will put larger contention window parameters, CW min, CW max. It will use larger values in the MUEDCA parameters so that it has a fair chance, right? Because it gave its airtime to the client. So it's therefore, if a client recently participated in triggered uplink, it's fair that client give back that airtime to the AP. So that is how this balance is achieved.
Understood. Now, since there are multiple users, I just have this question. In an OFDMA transmission, so is traffic of different access category allowed? So let's say station 1 transmitting voice traffic, station 2 transmitting video traffic, and also it's not necessary that all clients are at a same distance to the AP, right? One might be near and one can be far. Also different MCS set, is that also allowed in a single OFDMA transmission?
Yeah, so in theory it is allowed, okay, but in practice it is very difficult to do that. I'll tell you the reason. We'll look at two cases, right? One is we'll look at downlink case, right? So in downlink case, let's say we put different MCS for the different users, right? One is MCS 9, another user is MCS 2, right? If you try to put two different resource units, one in MCS 7, one in MCS 2, right? First question that will occur is, what transmit power we should use. Should we use the transmit power for MCS9 or should we use the transmit power for MCS2? Because generally we have different transmit power for the different MCS. Why? Because in Wi-Fi we have this transmit EVM requirements, and the transmit EVM requirements are different for different MCS. So higher MCS9 would require much lesser EVM. Like I forget the exact number. I think it is probably minus 30 dB EVM for MCS9. MCS2 would be like minus 10, somewhere around there. So you can tolerate a lot more distortion for MCS2, but MCS9 you cannot tolerate even the smallest amount of distortion. So if you use MCS2's transmit power, you will be violating the EVM for MCS9. If you use MCS9 transmit power, then the MCS2 user will have insufficient SNR to decode, because the receive RSI would be much significantly lesser. Because generally we have higher MCS will have lower transmit power and lower MCS will have higher transmit power. Because of this different EVM requirements, that is how it ends up as. Because more the transmit power, more the nonlinearity by the power amplifier, right? And all the components in the transmit circuitry, they will start behaving nonlinear for high transmit power. So if you want less distortion, you have to use low transmit power. So higher MCS will go in a lower transmit power, right? So because of this problem, practically if you see, the APs do not try to club different users with different MCS. So they'll try to club users of the similar MCS in a downlink transmission. So that is one of the constraints. Like, so really if you have a short range user and a far range user, you cannot really pair both of these things because of this EVM problem which exists. So that is on the downlink OFDMA. Now if you look at uplink OFDMA, we have different challenge. So let's say we have a short range user, then there's a far range user, right? So obviously and in Wi-Fi we have this habit of using the max transmit power all the time.
Okay.
Right? We don't follow this transmit power control. Like short range user means we use less transmit power. Far range user means more transmit power. We don't follow the distance based thing, right? In cellular actually they do it to save the battery life and all, they do it. Okay. But in Wi-Fi we don't do it. Reason we don't do that is because if you start using different transmit power depending on your location, you start creating hidden nodes. Because less transmit power means more hidden nodes. More transmit power means less hidden nodes. So you don't want to, so to avoid that complication, they always have the same transmit power. In fact, they prefer to have the maximum transmit power all the time, right? So if you have a short range user, he will transmit at, let's say, 20 dBm, right? Far range user also 20 dBm, right? But then path loss is different.
Yes.
Right? So far range user experiencing more path loss. Short range user experiencing less path loss. So if you look at the access point, it will receive two signals. One signal very strong and then another signal like weak. Right? So you have a weak signal. When these two get combined, right, and the AP has to receive them, it does not know what receive gain to use for that signal. Because normally we have to do this AGC, automatic gain control. So we have to choose the receive gain depending on the receive signal strength. If you have less signal strength, I will amplify more. If you have more signal strength, I will amplify less. Right? So that is how we are achieving the dynamic range of the receiver. So if you now bring in a strong signal and weak signal at the same time, which receive gain I will use? I have one receive gain I can use. So we have a problem here, right? So for this reason, APs on the uplink OFDMA also try to group users which will have like a similar receive RSI as seen by the AP. Okay.
Right.
Because otherwise, AGC will get the automatic gain control logic will get very, very complicated, right? Or what will happen is one signal will get buried in the other signal, right?
Right.
So the stronger signal will dominate everybody else, and the weaker signal will get quantized. As you know, at the receiver we have ADC, auto ADC converter, and digitize the signal. So if you bring a very weak signal and digitize it, it will get lost in the quantization, right? So quantization noise will be very high. So to avoid all these complications, both on downlink OFDMA as well as on uplink OFDMA, always try to group users with a similar MCS. So multiple short range users, together you can group it. Multiple mid range users, together group it, like that, right? So
Right.
group users with a similar MCS.
Yeah, understood, Susinder. Now let's talk about the benefits that OFDMA offers. So what are the benefits that the users can expect when OFDMA is implemented, and in what kind of deployments can we expect those benefits?
Yeah, so basically the scenario that is relevant for OFDMA is large number of clients, because that was the whole idea, right? The basic problem we are trying to address is in 11 AC, if you look at the throughput with respect to number of clients, as you scale the number of clients, the multi-client performance is not scaling very well. Okay. So actually there is a fundamental problem in Wi-Fi. Okay. This is present, all the generations, I would say. OFDMA tries to address that fundamental problem. The fundamental problem of Wi-Fi is efficient only if you use a lot of aggregation. So if you look at 11A and 11N, right?
Right.
Actually, for the same data rate, 11N will achieve almost twice the throughput. Simply because this has aggregation, 11A does not have aggregation.
Right.
So that aggregation makes a big difference. Why? Because in the PPDU, what we transmit, first we have to send 5 header.
Yes.
Then comes the 5 payload. That 5 header is pretty much a constant overhead. It doesn't matter what data rate you are using, whether you are using MCS 9 or MCS 0, same 5 header overhead will be there. So what happens if you are using a high data rate like MCS 9, your payload airtime will be very small, then the header airtime will start dominating. So that is why we do aggregation. So unless we do aggregation, what will happen is 5 header overhead will start dominating, right? So aggregation is therefore very important, right? But let's look at the problem in a realistic traffic scenario, right? Normally we have our, for example, MCS 9, 2x2 MCS 9, if you look at the throughput, that will be like, okay, more than 700 Mbps easily, right? So you have a lot of throughput, right? But how much traffic we have? If you look at our traffic, right? Normally, most of the traffic that we have, right, is like browsing HTML pages, websites, or WhatsApp, text messages, or even a voice call, right? Even if you take a voice call, it is all like, less than 1 Mbps, less than 1 Mbps of throughput, right? And this podcast that we are doing, right? If you try to look at the throughput requirement for this podcast, even if you take a HD quality, right? I would say within 10 Mbps, you can pack everything. Once you bring in the video compression and all, easily 10 Mbps will be sufficient for this, even for this podcast. So where is 700 Mbps? Where is 10 Mbps? Right? Yeah. So for all the traffic scenarios that we are having, most of the traffic scenarios, we are going to end up with very less aggregation, right?
True.
Which means we are underutilizing Wi-Fi. All the throughput numbers we are showing, right? 700 Mbps, 900 Mbps, that never happens.
Yeah, because
when you are using the maximum aggregation, yes, which is you're sending 64 MPDUs in a PPDU, at that time you get that throughput. But if I send only 2 MPDUs in a PPDU, what is the max throughput you can achieve? Actually, you should plot that and see,
Yeah.
you will see that the throughput will be very, very low, right?
Yes.
Even though you are using MCS 9 or even higher MCS, doesn't matter. Your aggregation is extremely low. Your 5 header dominates everything. So this is the problem. So with all the 11AC and previous amendments, we keep on increasing data rate, but real world throughput, we don't get anything because 5 header is dominating everything, right? So in practical Wi-Fi access networks, you go and see. Actually, this is one of the things I encourage all everybody, my students and whoever I talk to at go and look at the aggregation statistics on the AP.
Mhm.
So look at every PPDU, how many MPDUs are there. Just look at the histogram of it. See how much aggregation is going. Normally, right? The average, how much do you see? Do you see 64? What percentage of frames using 64? Right? What percentage of frames are using 1 or 2 MPDUs? You will see, you will be surprised. Less than 5 will be 90%. Less than 5 MPDUs will be 90%, which means your entire Wi-Fi efficiency is probably below 50%. And not probably, definitely below 50%. So we are heavily, operating in the worst possible region, right?
Right.
So that is one overhead. That is one fundamental problem we have, right? Second problem we have is every transmission we have to contend for the medium.
Mhm.
So
Yeah.
you have a large number of clients, right? They are all contending, right? Actually, there is a nice simulation we can do. So from the simulation, what we can see is once you cross 10 clients, the collision probability is 20%, more than 20%.
Right.
Okay. So which means if you're trying to transmit a frame as a client, there is a 20% chance it will encounter a collision.
Mhm.
Which means 20% of your transmissions are gone, wasted.
Wasted and collisions. Yes.
Because every time you have a collision, you have to retransmit it.
Retry. Yeah.
20% of your transmissions are waste, which means the time you spent wasted, the power you spent, the energy you spent, your battery drain, 20% waste, right? Remaining 80% is only succeeding,
Yes.
right? So a lot of airtime is getting wasted. In first thing is the random back off, because that is a constant that you have to listen before talk. So that is a overhead that is wasted. Secondly, even after all the random back off, there is a 20% chance you encounter a collision. So due to collision, you are wasting airtime. Due to random back off, you are wasting airtime, right? Then you are transmitting very less MPDUs in a PPDU. So the payload is also not efficient. So what you are doing, right? So it's very, very inefficient way of complete abuse of spectrum. If you have
Right.
to use the right thing, right? So people, that is why, right? People who work in cellular will say Wi-Fi is terribly inefficient. You are all wasting the spectrum. Give all the spectrum to us. We will make efficient, right? But anyway, jokes aside, right? So that is the problem. And with OFDMA, we can what do you say? We incur only one random backup overhead, right? So if you are, let's say, put 20 clients transmissions in one PPDU, I do random backup only once, right?
Right.
And then put together everything, right? So let's say everybody has only 2 MPDUs, right? But I have 20 clients. So 20 into 2 MPDUs will be 40 MPDUs. So 40 MPDUs will go in the PPDU. So the MAC efficiency, the efficiency of the MAC layer is now significantly improved. So I'm like most of the time operating at a much higher efficiency now, right? Compared to before, right? And then look at the uplink. Now that 20 clients can go together without any collisions, they are able to transfer
right.
to So that savings in the collisions also you are getting, right? So the 20% airtime which you wasted, 20% energy which you wasted on collisions, right? That random back of overhead, and then uh, 5 header, instead of sending like so many 5 headers, like one for every transmission, we have only one 5 header. Of course, it will be little longer because now we have to include that RU allocation information and all. And of course, in the uplink case, you have to send a trigger frame. But that overhead of trigger frame is kind of, we can share it across 20 users, right? It's
Yes.
like we're not sending one per user. So it is just one frame for multiple users. So that is amortized across all the users. So, so the best use case is basically all the traffic that we typically use day in and day out falls in the OFDMA use case only, right? Because most of the time we are sending text messages, and then like nowadays we are using a lot of this large language models, right? ChatGPT, Cursor, people are programming with it, right? So if you see, most of the internet traffic now is all prompts, all ChatGPT prompts, right? That is what is going on most of it. It's all if you look at it, it is text. It is text traffic only. So it's very little traffic. So rarely when we have a video call, okay, HD video is 5 Mbps. 4K video is 20 Mbps. Okay, how many people use 4K video? Very less, right? Now very rarely we'll download some file. Okay, so at that time it will be like lot of traffic. So if you're downloading, say, a large file, yes, but how often you do that? So that is pretty rare, right? And then emails, most of the emails without attachments. So that's also very, very less traffic. So 90% scenario is perfectly suited for OFDMA, right? And today, if you see, you go to any home, in the US, I can tell you the average number of clients in a home is 20. Wi-Fi, I'm saying. Average number.
Yeah.
In my home, I have crossed 30 now. Right?
Wow.
So we have because one home, each individual has phones. Some people have 2 phones, right? Then you have laptops, right? Then you may have a desktop, right? Then we have lots of this IoT devices.
Yes.
Everything is coming with the Wi-Fi integrated. Electric vehicles have Wi-Fi integrated, right? TVs, all the TVs now come with Wi-Fi, right? So
Right.
if you now see, right, average number is exceeding 20 in the United States. Now I think the same thing in different countries. I think the number of Wi-Fi clients is growing every day. So more clients and then very little traffic for lots of clients. Perfect fit for OFDMA.
Right. I think very well described the use case. Now let us talk about the scenarios where OFDMA wouldn't provide much benefit, or even may introduce additional overhead when compared to normal cases.
Yes. So there is two reasons I can give. One is, in the standard itself, they didn't do certain things correctly, in my opinion. Okay. One aspect, I think maybe it is unavoidable. When they're creating this resource units, right? So when you're splitting an 80 megahertz, for example, into smaller resource units, the more you split, what happens is they have to introduce some null subcarriers, what are called null subcarriers. So not all the subcarriers can be used, unfortunately.
Okay.
Some of the subcarriers you have to give up when you do OFDMA. Okay. That will cause a reduction in the data rate. Okay. 5 data rate will go down. It can go down up to 18%, worst case. Okay. It can go down up to 18%. Okay. Typically will be like 10% you can go, right? On the average, it will be 10% it will go. I think the best case is like 5%. So 5% to 18%, somewhere there, you are going to incur a reduction in the data rate.
Right.
Right? So this is I think unavoidable. I'm sure this whoever contributed to the standard, they would have looked at all the possibilities, and this is something that they could not avoid. Okay, so this part I understand this. So let's give 10 to 15% loss, right? So starting itself 10 to 15% loss, right? But imagine all the other all the other problems I mentioned, right? You're always operating in 1 or 2 MPDUs, considering the 5-header overhead, and still there is opportunity for gain, right? So because of this 15% lesser data rate, if you are trying to download a file, so that is like large number of MPDUs per PPU, right? So that's a high throughput scenario. So in a high throughput scenario, like a file download, and in that scenario, OFDMA will be negative, will have a negative gain. It will not give you the best result because you're going to be 15% lower data rate. So directly it will hit your throughput 15%. Okay. And you are using 64 MPDUs per PPDU, right? So in that large payload airtime, right? So when the payload airtime is large, right, OFDMA is not very helpful. Okay, in fact, it is consumes more airtime, right, or gives you lesser throughput, right? So, but that is not majority of the scenario. I mean, majority of the traffic. That is my point. I mean, majority of the traffic is very little. What do you say? As I said, less than 5 MB of throughput. That is the majority of the scenario, right?
Yes.
So this is one case where it is not helpful. Another problem which could have been avoided, in my opinion. So this is, I would say, lack of foresight, or they didn't think about this when they wrote the standard, is the RU allocation is very complicated in Wi-Fi. Reason is they have this constraint that one user can be allocated only one RU. You cannot assign multiple resource units to the same user. So, which means I have to either assign RU26 or RU52 or RU106 or 242 or 484 or 996. Only these choices I have. That flexibility in the RU allocation is limited, right? So, what I would have preferred is have only one RU, which is RU26. Okay. And then allow multiple RUs per user, right? So then one user can have 2 RU26 or 3 RU26 or 10 RU26. All these options become possible. Your allocation becomes a lot simplified, right? Now you created this like a cash currency change problem. You go to a store with the cash and buy something, right? He will tell you $39. Okay, there is no $39 currency.
Yeah.
You have to figure out how to break up and then somehow achieve that 39 with the existing currency notes that you have, right? It's not a very straightforward exercise. Okay. So imagine we have to do this RU allocation for lots of clients, right? And if you are going to end up with a lot of CPU cycles just to compute the RU allocation, forget about sending OFDMA and all. First of all, before sending OFDMA, I have to decide which users have to be target. Secondly, I have to allocate the RUs for them. Okay. And that RU allocation has to be based on how much traffic requirement is there for each of the users. So typically, we don't know exactly the traffic, what the user is using, but what we know is like the queue size. So all the traffic will come first, they sit in queues, right? So whichever has a lot of queue size, we'll try to allocate more RUs for them, right? So, but we don't have that much flexibility in RU allocation. So as I said, we have only like certain fixed units, and that really complicates the RU allocation algorithm. Because of this, what has happened is the chipset vendors who design the Wi-Fi chipsets, they have not budgeted enough CPU cycles to do all this computation. Because you're now asking me to do 20 clients computation for 20 clients, and that has to be done in like few microseconds. Do we have that kind of compute available in the access points today? Not really. Okay, we are running like very, it's very less compute that we have on access points today. Okay, and memory also is a problem. Two problems. One is you don't have that much memory, and then you don't have that much CPU cycles also available. Okay, so this is something I think the standard people did not foresee, because usually people who work in standards don't work in products. That's unfortunate reality. If you see, right, people who work in products will not work in standards. People who work in standards will not work in products, right? Because company each person has to focus on different things, right? So just like a programmer does not generally do testing, we have a separate test team, and then you can argue why not same person do everything, right?
Yeah.
Right, like Candela is trying to do, same engineers do marketing, sales, and engineering, right? So there is revolutionary thoughts are there, but I'm saying, right, today in the world generally we have this compartmentalized thing, right? Test team, that like that. Unfortunately, in many companies we have standards team, we have product team, right? That is okay. I'm fine with that. But what I'm not fine with is standards team not talking to products team, or products team talking to standards team. That is a so, in my opinion, if these two teams had talked to each other, and the product team would have told them, hey, we don't have so much CPU cycles to run all this complicated RU allocation algorithm. So try to make it simplified so that we can do with less CPU cycles, right? If that conversation had happened, I guarantee you they would have gone with a single RU allocation. I mean, single RU size, like RU26, and then just allow any number of multiple of RU26 for each user. That would have greatly simplified OFDMA, and if that had happened today, OFDMA would have been the talk of the town, right? The reason it did not happen is because of this mistake. I would say, honestly, in my opinion, it is a mistake, and unfortunately, it is still not corrected. Even Wi-Fi 7 is not corrected, and I don't see any correction in Wi-Fi 8 also coming in this. But hopefully, people listening to this podcast will think about it, right? So, because of this, what has happened is practically the OFDMA. Are we achieving the best OFDMA results? Answer is no. And the reason for it is we don't have the proper compute budget available for it. People who design chipsets did not put in the appropriate compute for it, right? Now, if in future that compute problem is addressed, for example, you put a NVIDIA graphics card on a access point. Actually, this is one of the experiment some people are trying actually. So instead of using a normal processor, put a GPU. Okay. So it do a lot of parallel processing, right? And it can run a lot of this artificial intelligence algorithms, right? Neural networks and all, right? So this RU allocation and all, very good candidate for doing artificial intelligence, neural networks. So you can do the RU allocation algorithm completely with the neural networks. That would be like awesome. But yeah, it's all possible in theory, but we need that much amount of compute, which will increase the cost of the access point. So who will bear that cost? Nobody is willing to increase the cost of the access point, right? So all the generation keep coming. But if you see the cost of the access point, it's kind of saturated, right? We're not able to go beyond a point. People are like, you give me whatever Wi-Fi it is, I will pay only so much. Right? Whether it is Wi-Fi 7, 8, 5, 4, I don't care. This is all I can pay, right? So today, Wi-Fi to some extent has been like what he says, commoditized, or the price you are not able to raise beyond a point, right?
Right.
But hopefully, the cost of chipsets also do come down over time, right? So let us hope. Uh, I think despite all these things, right, OFDMA is showing gains. Okay, in the field, in practice, it is showing gains. My only point is, it is not at the point where it should have been, right? And
Understood.
that's
Yes.
because of all these mistakes which has happened.
Understood. Now, the next question is about the gains that you are talking about. So, what is today's adoption on OFDMA look like? Are enough APs and clients embracing OFDMA that are coming out?
Yes, so actually OFDMA, one good thing that happened, which I really appreciate, is Wi-Fi Alliance took a stand. Not only, Wi-Fi Alliance or the organization took a stand, all the members of Wi-Fi Alliance also were united that OFDMA should be mandatory, right? Not just in Wi-Fi Alliance, even in IEEE standards also, it is mandatory, right? And for Wi-Fi Alliance certification also, OFDMA is mandatory, right?
Okay.
So I really like that and really welcome that, because what actually one of the disappointing aspects of Wi-Fi, I would say, is there are so many features in the Wi-Fi standard. Okay, only 30% of them gets implemented. 70% of them is not implemented at all. Right? So what is the point of writing on that big standard document? I don't understand. Like 70% of it is waste. So there is big disconnect between what is happening in the products and what is in the standard. Right? So I really, I like the idea of making things mandatory. Okay. I don't like this optional thing.
Right.
Simply because every time something is optional, some people will implement, some people will not implement, which means interoperability is a question mark.
Yes.
Right? Interoperability is there means then you cannot sell that feature in the market. Right? I can show you lab demos, but I cannot really show you a real world benefit of it. Right? Unless there is interoperability. So interoperability is very important. So that way I really welcome OFDMA is required for certification, both as an access point as well as a client. If you want to get certified, OFDMA is required. So adoption, everybody who has certified has to adopt it. There is no choice. Okay, there are in fact like counter opinion. Some people argue, hey, for IoT devices, you should have given exemption. IoT devices, they are really, they're cost constraint. So you're asking OFDMA and all these things, it is increasing the cost of IoT devices and it making it. Okay, I think I understand that point of view. Like if you are very occasionally sending lights on, lights off, this kind of messages, we probably don't need OFDMA for that, right? But anyway, generally I like this idea of having it mandatory. So that part is there. Okay. So they are certifying, that's all there. But is it getting used? That is different question, right? Device supports it. Yes. Support is there in pretty much all the devices, Wi-Fi 6 devices, they are supporting it. But usage is different. Okay. So first of all, as we discussed, for large payload airtime, OFDMA has a negative gain. So it does not make sense to use OFDMA for large payload scenario, right? Only for small payload scenario, it makes sense. So which means you should not blindly always use OFDMA scheduling. We have to use single user scheduling for all these large payload scenarios, right? And for small payload scenarios, only then we should use OFDMA, right? So that is one part. Another part is these OEMs, client, especially smartphones, product OEMs. Like I'm not saying chipset vendors. Chipset vendors are all supporting all these things. Product OEMs, especially smartphone side, have somehow developed this understanding that OFDMA is not a good idea. Okay. I don't know exactly why, right? I've talked to a lot of people in the industry. That is probably a topic for a different, another podcast, right? But clients feel that, especially triggered uplink, they are losing control.
Okay.
They are losing the freedom to decide when to transmit. So let's say a client is like, he's going to wait for this trigger frame, right? So normally before, OFDMA, if client has any package to transmit, it will right away content for the medium and transmit, right? Now you are saying, you don't have to do all that. AP will send trigger frame. You will be given a time and you just transmit that, right? That's what we are saying, right? Now, if we believe that, that is good, right? It's good for everybody, good for the individual also, right? But clients think otherwise. They're thinking they want to have the control. They want to have the freedom and flexibility to decide when they want to transmit. And they have doubts. Okay, the doubt I have is, okay, what will this AP behave fair to me?
Mm-hmm.
What if he does not give me a fair chance?
Okay.
Because if I submit to his demands, then he's going to decide the RU allocation for me, right? So I cannot decide for myself. He's deciding for me. That is fundamentally some client product OEMs are against this idea. Okay. Another problem I'll tell you. Again, this is all coming from conversations which I had with several smartphone OEMs. I don't want to name the specific companies, but I think the point is important. They somehow think OFDMA is detrimental to battery life.
Okay.
And this is the example. One of the my friends in that company suggested. So let's say you are having 80 megahertz. AP and client are connected in 80 megahertz bandwidth. Now, if I do OFDM, client can transmit whenever it wants, first point. And then it can use 80 megahertz bandwidth. Right? So let's say I have, as you say, small payload airtime scenario, right? I have less than 1 Mbps of traffic.
Mm-hmm.
Okay. So if I do 80 megahertz bandwidth, what I will do is I will use 80 megahertz transmission. So my airtime will be less, transmit airtime. I will transmit that and go to sleep. Right?
Yes.
Now, if I, let's say, do the same in OFDMA, right? Now, instead of 80 megahertz, now I will be, clubbed along with several other clients, right? Which have 1 Mbps traffic, right? And now I will not be assigned 80 megahertz bandwidth. I will be assigned maybe 20 megahertz or maybe even 2 megahertz, right?
Yeah.
So let's say 20 megahertz, right? Just for example, right? So instead of 80 megahertz, you will allocate 20 megahertz to me and 4 users together are transmitting 20 megahertz to each, right? Which means my airtime is now 4 times higher now. Right? My transmit airtime is now increased to 4 times.
Right.
Which means, I am transmitting for a longer time on the medium. I could have slept in that time. You understand? They think that because you are allocating lesser bandwidth, my airtime has increased, my transmit time has increased, which means my energy consumption will go up. Right? Okay. I don't agree with this view. Okay. That is a different point. The thing is, your other option is going with 80 megahertz and colliding 20% of the time.
Right.
So people are not looking at that.
They're not saying at the efficiency of on the network side that OFDMA offers.
Correct.
They're only seeing on the client's perspective.
Yes, you are looking. First of all, your thinking is selfish, right?
Yeah.
So secondly, right? everybody is now creating overhead on the medium, and that brings down the available airtime for everybody.
Right.
Actually, it hurts everybody, right? Then you think you're transmitting 80 megahertz bandwidth, right? I mean, that point you agree, right? 80 megahertz, if you transmit, you will consume lesser airtime, you can go to sleep in the remaining time. So your thinking is maybe you can sleep longer. But actually what is happening is, in your attempt to transmit 80 megahertz, 20% you will fail.
Yes.
Right? And then you will retransmit. So that battery life is wastage.
Yes.
Right? So if you see net, I don't agree that OFDMA fundamentally increases the energy consumed or brings down the battery life. So this is I would say this is a wrong understanding, that OFDMA will bring down battery life. So because of this belief, along with the intention to have control over when to transmit, right, and not give it to the AP, right, clients do not want to participate in triggered uplink. Some clients, I don't want to name particularly which clients,
Right.
some clients do not like to participate in the triggered uplink. So what they do is they either go and indicate to the AP that they don't want to participate in triggered uplink. Further, there is another feature called operating mode indication, OMI. Okay, so they can use OMI and tell the AP, I don't want to participate in triggered uplink. Either they do that, or there is another thing that APs, if they, especially for uplink, if you want to schedule, APs need to know the queue size on the client side.
Right.
Right? Then accordingly only we can allocate RUs. So clients have to send what are called buffer status reports. And these buffer status reports, if they are not sent properly, AP will not know what is going on the other side. Like how much traffic is there, how much queue size is there. So it cannot do the RU allocation properly. So if the clients don't send the buffer status reports, then the AP will not really schedule for it, right? Or even if it schedules, it will not be like fair, right? So this is another. So in terms of adoption, you asked adoption, right? So this is practical usage is facing all these problems. I think first problem that needs to be fixed is this perception that some smartphone OEMs and client OEMs are having, that OFDMA will bring down battery life. That perception has to be first corrected. Secondly, they think they having all the control is good for them, right? That is another thing, that myth has to be broken, right? So because they have to see what they are gaining. So unless they see a gain, they are not going to come to the OFDMA. So, and thirdly, not many people have actually published OFDMA benefits with the real products.
Right.
So people have to see the benefit. See, people will opt for change only if you show them the benefit. If you're not showing them the benefit, and of course, when the standard was created, they showed a lot of simulation. I'm sure there are all those simulations exist today. But that's not enough. You have to show with the real products. You have to show that it actually happens in real world. Then only people will believe. So I think more people have to publish these results of OFDMA gain. People have to engage in these conversations. Hopefully this podcast is a starting point, and people will start thinking about all the points that we discussed in this podcast, and probably they'll reconsider.
Right. Yes. Now talking about somebody has to show the real benefits. So how would you suggest that someone has to practically show the real benefits? So what would be a good test case to test OFDMA and show good results?
Yeah, so this is the topic actually which I talked about recently in the Candela Tech Summit, which happened in Bengaluru, I think just a few weeks back. So there is a detailed talk just on this. This was the main focus of the talk, right? But for the purpose of this podcast, I'll just briefly summarize that, right? So the idea is first you have to create small payload airtime, okay? And then you have to, good use case would be like 80 megahertz bandwidth. So you have high data rate, but then you create like few MPDUs only per user, right? So create 1 Mbps traffic. So 1 Mbps traffic to, let's say, 10 or more devices, right? Actually, in the Candela Tech Summit, we shared results with 14 clients, 14 OFDMA clients we connected. I mean, from Candela team only, they did all the testing and the results were shared. So thanks to Candela again. So Srisha, actually, she helped collect some of that data. So 14 OFDMA clients, each having 1 Mbps traffic and sending uplink traffic. Okay, uplink traffic 1 Mbps for 14 clients, and all the clients are connected in 80 megahertz bandwidth. Okay, and we had all the clients like short range in a shield room. We had AP and all the clients in one shield room. So it was pretty much all the clients were getting the max MCS. Okay, so high data rate, 5 data rate, but then the payload airtime is very, very small, like 1 Mbps, right? So the benefit of OFDMA is airtime, right? You're going to save a lot of airtime. If you opt for single user scheduling, then all the 14 clients have to fight for the medium. They'll waste 20% airtime in collisions, and then when they transmit also, random backup overhead is there. Then ACK, everybody has to send ACK separately, and then 5 header overhead is there. All these overheads come, right? When you do OFDMA, one trigger frame, all of them come together, one transmission trigger based PPU, one multi-star block hack, finished, right?
Right.
So overall, if you see for the same traffic, right, which is you're sending 1 Mbps to 14 clients, which is roughly 14 Mbps aggregate throughput, right? If you look at the airtime utilized, the utilized airtime is going to be lesser in the OFDMA case.
Yes.
So contrary to the expectation, you remember I was talking to my friend and he was telling OFDMA will decrease the battery.
Yeah. Yes.
Because he thinks 80 megahertz bandwidth, I will finish my job quickly and go to sleep, right? But
Yes.
what is happening? Total airtime consumed with OFDMA is lesser, which means clients have more chance to sleep now.
Right.
It's quite the opposite of what he was saying, right? So that is one aspect, but the way we showed the benefit was we are showing what is the unused airtime, what is the leftover airtime, because what is used is going to be brought down by OFDMA, which means what is leftovers will be more. So when you have more unused airtime, what is the meaning? Somebody else can use it. More people can use it. Maybe another AP on the same channel can use it.
Right.
Or other clients connected to that same AP can use it. Right? Because all this 14 client traffic is now consuming lesser airtime. Right? So the way we showed is like the problem, one of the reasons I think why Wi-Fi 6 came in, I think 2020 so I forget the exact year, but now 2025. 5 years, I have not seen any OFDMA benefits results publicly shared, especially with respect to like airtime, showing these benefits. So I think one of the reasons is we don't have tools to measure that airtime. We don't have tools today that tell, okay, how much random backup airtime was gone, how much 5 header airtime went, how much payload airtime went, how much block hack airtime went. We don't have this kind of tools, right? So because of that, people didn't know. First of all, I mean, this scenario everybody knew, small payload airtime OFDMA helps, but show me how much it helps, right? So that we could not bring it out because we could not measure these things. Okay. So one idea what we showcased in the Tech Summit was that unused airtime, let that unused airtime be used by some other client. So what we did, we connected a 15th client, which is non-OFDMA. So it is Wi-Fi 5, So it will not participate in the OFDMA. And then we run unlimited UDP uplink.
Okay.
So what will happen is whatever airtime which is not utilized by the 14 clients, the remaining airtime will be completely utilized by the
Yes.
15th non-OFDMA client.
Yeah.
So if you go and measure the throughput of the 15th client,
It
that
should
is
be higher.
proportional to the unused airtime, or it is going to be higher in the OFDMA case.
Right.
So we basically showed the results OFDMA enabled on the AP, OFDMA disabled on the AP. What is the throughput of the 15th client? Okay, and we could see more than twice the throughput. Actually, a lot more. If I recall, like 4 times or something, right? So it's like significant throughput benefit they could see, right? This is one way of just showcasing the benefit, right? So if you want to do a demo or tell or show this benefit to others, I think this is a very good way to showcase it, right? And it also dispels the myth that people think OFDMA will make the battery life worse. Actually, OFDMA can potentially, improve the battery life because your consumed airtime overall has been brought down, right?
Right.
So I think a lot more people need to do this test. Of course, as a first step, Candela has done it, and hopefully it will be published soon. But I think others also have to do this.
Right.
So many other companies have to do the same exercise, and they should be able to verify it. They should be able to see the same benefit. And when everybody has seen it, then that will cause the change. I'm sure it will cause the change in the mindset of the smartphone OEMs. Because right now what's happening is some of them have gone and disabled it, or they don't want to exercise it, right? So now they may reconsider that decision.
Yeah, thank you for explaining it in a very detailed way, Susinder. So now, probably the last question. So if I'll give you a set of features in Wi-Fi, and you had to rank them. So basing on the contribution to Wi-Fi. So the first one being the making the significant contribution, and the last one being slightly lesser. Here we go. The features on my list are frame aggregation, and then MIMO, MU-MIMO, OFDMA, BSS coloring, and then MLO.
Okay. First, definitely I will give it to frame aggregation, because without that frame aggregation, all the increase in modulations that we did, that would not have converted into throughput. So frame aggregation definitely is I would rank it number 1 in the list.
Right.
Number 2 is definitely MIMO. Because MIMO helped increase the spectral efficiency, right, of Wi-Fi. So we could get more throughput with the same bandwidth, right? And not only that, MIMO also helped with the diversity. So all these products, right, they are quite a bit of sensitive to the orientation, antenna orientation. So, and even you can see that you have the phone, sometimes in one orientation you have a good experience, you just put it in a different angle, and then you see the throughput completely changes. The reason for that is antennas, right? Antennas have something called polarization. So either it's vertically polarized or horizontally polarized, right? So it's only one polarization, and then there's the concept of circular polarization also. But there are different 2 polarizations that can be there. Only 2 polarizations that we can have. So if you had your antenna vertically polarized, and if the electromagnetic signal, that is electromagnetic wave that is incident on the antenna, right, that is horizontally polarized, it's in the different polarization, then you will get less signal strength. So that is why when you change the angle of your device or the orientation of your device, your RSSI, receive RSI completely changes, and the throughput completely tends to change. Now with MIMO, since we have two antennas, and what most products do actually is they place the two antennas in different orientations. So you get that orientation diversity. So even if one of the antennas is in like a deep fade or something, the other antenna will get a good signal strength. So in that way also, MIMO has helped. So that is why you see all the smartphones today, or pretty much all the clients have migrated to 2 by 2.
Right.
You no longer see 1 by 1 devices. It's very less. Even IoT devices are having 2 by 2. Okay. Some of them, right? The reason for that is the benefits of MIMO. So MIMO definitely, the kind of high throughputs we are able to achieve, pretty much close to Ethernet throughput. Like Ethernet giving 1 Gbps, we are now talking several Gbps throughput in Wi-Fi. So MIMO made it possible. So definitely on the two ranking, second I would put MIMO. Now third, probably I would put OFDMA. I would put OFDMA, right? OFDMA, because why? Because it is aligned with the practical traffic scenario. Most of the traffic scenario that we are talking about is small aggregates. So which is the perfect fit for it, right? Of course, it could have been done better. The RU plan and all could have been done better. RU allocation could have been simplified. Yes, but despite all those things, the intention was correct. It addressed the right use case. It was the need of the hour. So, and there are gains. We have demonstrated the gains also. So, third, I will put OFDMA. Fourth, I will put the MLO. MLO, I will put that, because MLO simplified that band steering. Clients are able to steer between the bands very easily without having to do four-way handshake once again. With the same encryption keys, they can go back and forth between links, and it helps with congestions. If there is a congestion in one link, you can send that frame on another link, right? And then it helps. The diversity of links helps. Of course, if you had two radios, you can even get higher throughput. But I know most of the clients do not have the two radios; they have only single radio. But despite it, I think it's a good idea. MLO is a good idea, and it is helpful. It is helpful in a practical scenario, especially with congestion, and congestion is becoming a problem actually. So definitely next on the list is OFDMA. Last on the list, I will put MU-MIMO. The reason for it is MU-MIMO in theory is great. Okay, it works great. In practice also it works great, but it has some prerequisites. The two prerequisites for MU-MIMO to work well. One is, obviously, you need to get good quality channel sounding feedback, that CBF reports or compressed beamforming report. We have to get the channel estimate from the clients. That has to be high quality channel estimate. So it incurs quite a bit of overhead to do that, right? So, but if you get that sounding done correctly, then you can have much higher throughput possible. But second prerequisite for the MU-MIMO to work is the AP needs to have more antennas than the number of spatial streams it is transmitting. So, for example, if you have two clients and I'm trying to do MU-MIMO to two clients, and both the clients are two spatial stream each. So, two spatial stream to one user, two spatial stream to another user. So, totally AP is transmitting 4 spatial streams. So, AP needs to have more than 4 for this to work. Okay, so for this to work properly, because I don't want to get into the details of the mathematics and all, but that is a kind of requirement. At least you need to have one more antenna compared to the number of spatial streams that you are transmitting, which means AP should have minimum 5 antennas, right? And we don't have 5 antenna APs today. I mean, most APs we see are 2 by 2, right? Some of them are 4 by 4, or some may be 3 by 3. but very few are above 4. Actually, there are few APs in 8x8. I actually personally have worked in 8x8 AP productization. So, in my previous company at Ruckus, we actually had a 8x8 AP. They still sell it actually, but the market didn't receive the 8x8 very well. So, if you have a 8x8 AP, it works, MU-MIMO works very well with the 2x2 clients that are out there, right? Which pretty much not many APs are doing it. So it's not, the market is not there for it. That is what I can see, right? So given we have 4x4 APs and most of the clients have become 2x2. So now with 2x2 clients, it will not work. So practically you don't see it working. Okay, people say it doesn't work at all, which is not true. If you had 8x8 AP, it will work very well. And, maybe another opportunity, we can even do that test and we can share the results. So 8x8 AP with 2x2 clients, MU-MIMO works very well, right? And of course, you need to have limited mobility. If you have too much mobility, then the channel sounding overhead will be very high, right? So that's another thing. So as you can see, right, limited mobility should be there. AP should have a lot more antennas, right? And then good quality sounding has the CBF reports have to be obtained. You have too many prerequisites,
Right.
And it's like so many stars have to align for it to work, right? When so many stars, what is the chance of aligning? It's very less. So practically, the benefits have been very less. But in theory, definitely it's there. And as I said, 8x8 AP, it still works. Maybe in future, if 8x8 APs were to resurface or people start to adopt 8x8, maybe 6x6 also good enough, or 5x5. I don't know why they went directly from 4 to 8. Why not 5? I don't know. So yeah, that is a reason for me putting MU-MIMO. And MU-MIMO is actually helping with the large payload airtime scenario, which happens very less time. Like what the percentage of time you actually running that much amount of throughput. So for 10% of use case only, that probably fits. So that's why I'm ranking MU-MIMO the last.
Understood. Maybe one last concluding question. So you have mentioned that now the devices are increasing in every home. An average US home has 20 or probably more. You have 30. So I have seen few IoT devices myself, which are coming just with N standard capability, not even AC. So do you think such devices should actually embrace AX and include OFDMA so that they can participate in the overall network efficiency gains that we are talking about?
Now, see, IoT is like a little broad term. Okay, I would like to, properly classify this IoT. Okay, see, if you take a light bulb or a plug, electric plug, which can be Wi-Fi controlled, these are one class of IoT devices. Okay, where it's like very rarely you have some traffic, right? Or you have like a temperature service, like a thermostat, right? A Wi-Fi based thermostat, right? So these have very, very little traffic, very rare, right? So for these devices, I would not like to burden them with OFDMA and all these things. Okay, they don't, because this is so rare traffic.
Right.
So for these devices, cost is important. Like on a light bulb, I mean, thermostat, maybe if you add a couple dollars, people will not mind. But on a light bulb, if you add a couple dollars, that product you can't sell it. So cost is a challenge. Okay, and certification pain also. People have to go and get Wi-Fi LAN certification. Wi-Fi LAN certification costs money. Actually, that's another thing. I think for the good of the industry, Wi-Fi LAN needs to bring down the cost of certification, because otherwise what will happen is people will stop doing the certification to save money, right? To save money, they don't do certification, and that really hurts the industry overall. So, I mean, it is my appeal to Wi-Fi Alliance that they should look into ways to bring down the cost of certification so that more devices can get certified and not less. Right. So this is one class of IoT device. For this, my personal opinion is don't burden them. They need to be cost optimized. So go for 11N or even lesser technology, right? For them, power consumption is also important. Of course, light bulb is powered, so that's not a issue. But we have some cases where, for example, a doorbell.
Yeah.
If you talk about a doorbell, we would like it not to be like wired to the, electricity, right? So in fact, there are like creative ideas, like every time somebody presses the doorbell, you are creating a mechanical energy. And what if we can convert the mechanical energy to electrical energy and charge the battery, right? So that it can run infinite. I mean, nobody has to sit and charge it, right? So every time somebody keeps pressing the bell, it will keep on working. So these kinds of devices, battery life is very important. And for that, right, your power consumption has to be significantly reduced, and cost also has to be reduced. So for these class of devices, I would not really push them towards OFDMA. If they want, they can come, like leave it optional for them, right? But there are another class of devices like cameras. People call IoT camera also as IoT devices. So I don't know. So that's why I wanted to make that distinction. So like cameras, outdoor cameras, indoor cameras, they are transmitting like 5 Mbps, 10 Mbps of traffic. If you have 2 cameras, it will be even more. So these kinds of devices, and they are typically battery operated Apple. Okay? They can benefit with OFDMA.
Right.
Okay, because they can save airtime by sending that 5 Mbps of traffic with OFDMA. They can do it, and they can potentially benefit. Potentially, there is a benefit that they can reach, and I think these devices, they can consider OFDMA, and they can also afford that little bit higher cost. Cameras are sold for like pretty expensive actually. So so I think it is worth for them to consider Wi-Fi 6, go for a higher bandwidth, right? Because that way they can quickly finish what they're doing and go to sleep, and OFDMA gains also are better with higher bandwidth. So these class of IoT devices, yes, not for the light bulbs and doorbells and all. I mean,
Right.
of course, doorbell with camera is different.
Yeah.
So you put a camera there, then I would say OFDMA, yes.
Yeah. Understood. So that's all for today's episode. Thank you, Susinder, for sharing all your wisdom with our audience. And it's not just theoretical, guys. He also shared his practical insights as well from the industry, from his friends. So please do watch this episode, and if you like the episode, please leave a like. And if you have any questions to Susinder, please leave them in the comments so that he can address your queries. And like, share, subscribe, and please stay tuned to Weekly Wi-Fi Wisdom for upcoming episodes. Thank you so much for watching, and thank you for giving us your time. See you in the next one. Thanks.